Okay, so what I want to talk about in this lesson is this idea or this technique that's known as spectroscopy. And spectra relates to light, and scopy kind of relates to look at or measure. So if we take an atom, so if we have a look here, so this kind of represents an atom. So in the middle you have the nucleus, and then you have an electron here that's in a space that's just outside the nucleus of the atom. And what happens is when a photon or a wavelength of light strikes an atom, if that photon or wavelength of light has just the right amount of energy, what it'll do is it'll cause the electron to move up into a higher energy level. So it'll go from, so imagine this is the electron, it's moving around in this space, it absorbs some energy, and what will happen is it'll move up into a higher energy level. And when it does that, what it actually does is it absorbs that wavelength of light, and the electron gets some energy, and then it moves up to this higher energy level. Now, atoms will, like electrons, for example, depending on the level they're in, they will only absorb very particular wavelengths or photons that have a particular amount of energy. So it has to be an exact amount. And what happens is then when it's up in this higher energy level, it's unstable and it stays there for a while. And then what happens is it actually moves back down to its original energy level. But when it does that, it gives off a wavelength or a photon of light that has the same energy as the wavelength or photon of light that that struck the atom or was absorbed by the atom. So basically, the idea is that elements on the periodic table, they can absorb um, particular wavelengths of light or particular colors of light, if you like. So if we have a look here, then what we have is this is what's known as a continuous spectrum. So we can see here we have colors, for example, from red to yellow to green to blue. And each of these wavelengths of light are associated, each of these colors have a particular wavelength or a particular energy that's very specific to it, and that's what gives it or makes it, it has its particular color. So what we have here is what's known as a continuous spectrum. So this is like a rainbow, for example. If you take white light and you pass it through a prism, like a piece of glass, for example, it'll break it up into, it'll bend all of the individual wavelengths of light, and what will happen is you'll get this what's known as a continuous spectrum formed. And this is what happens when a rainbow is formed as well. You get this white light that has all of these colors of light within it, and it is broken up, let's say, or split up by raindrops in the sky, and it causes the white light that contains all the colors of light to be split up, and you can see all the individual colors of light. So that's like the rainbow effect. Now, remember, each of these colors of light, they are associated with a photon that has a particular amount of energy. Or another way to think about it is it's associated with a wavelength of light that has a very particular amount of energy that makes it unique. So what happens then is if you were to take, for example, a hot gas, like for example, if you were to take a hot gas of hydrogen, for example, if you heat up this, if you add energy into all of the atoms that make up this gas of hydrogen, all of the atoms, the electrons are going to get excited and move up to a higher energy level, and then they're going to move back down again. And when they do that, they're going to give off particular wavelengths of light. And that's why when you see, if you have a hot gas, for example, of hydrogen, you add energy to it, all of the electrons get excited, move up to higher energy, move back down, and then give off particular colors of light that are very unique, and they're like a fingerprint to that particular element. And what will happen is you'll get this effect. So you're only going to get very specific wavelengths of light. And this is what's known as a emission spectrum, because basically the atoms are emitting particular colors of light because they're heated up or they're excited, they've been given an amount of energy. So you get this effect, what's known as a spectrum, and that spectrum can tell you the types of elements that are present within that gas, because they give very specific bands like this. And the other thing that can happen is if you take white light that contains all the colors of light, and you pass that white light, for example, through a cooled down gas of hydrogen, for example, it can be any element that's in gas form. What's going to happen is, and then you pass that through a prism, it's going to give you a continuous spectrum, but it's going to take out the specific colors or the specific wavelengths that are absorbed by, for example, the elements of hydrogen in this case. And you'll get this effect, you'll get a continuous spectrum, but you'll get these lines or bands that are missing, or these colors that are missing. And the reason they're missing is because that white light, before it went through the prism, it went through a particular gas cloud, and that gas cloud, for example, if it's a hydrogen gas cloud, for example, it's going to absorb the very unique wavelengths of light that are unique to hydrogen, that are absorbed by hydrogen, and you get this, what's known as an absorption spectrum. So basically what we can do is we can take light from the stars and we can pass it through a prism, and we can get these kind of effects. We get these what are known as spectrums, and this is the process, or what's known as spectroscopy. So if we look at this, so when we examine the light that's coming from the sun, we get this kind of effect here. So we get like a continuous spectrum, but there's particular bands, if you like, that are taken out or absorbed. So what I want to do is just to kind of explain where this comes from. So if we take, for example, we have the sun, so we have the core of the sun. So this is the core, and fusion is going on in here. It's going on within the core. And so imagine this is your core. So what's happening is it's giving off, this process in the core is giving off photons of light. And it's giving off, or wavelengths of light, you can even think about it as well. And it's giving off all the wavelengths that are associated with all the colors, for example, in a continuous spectrum. So all of this light, if you like, all the colors of light are being passed out of the core of the star. And what happens is they go through the atmosphere of the star. So imagine this is the atmosphere. So this here is the core, this is the middle, and then we're just looking at a cross section. And what's happening is all of this light energy, or white light, that contains all of the colors of light, it's coming out. So because the fusion process is generating all of this white light, what's happening is this light is passing out here into the atmosphere of the star, of the sun, for example. And within this atmosphere of the sun, you can have all different elements within it, elements that have been formed through the process of fusion in the core of the star. So you might have, for example, you could have hydrogen, and you could have sodium, Na, sodium, you could have oxygen, you might have iron, you could have calcium, Ca, and so you could have all of these elements that are present. And what actually happens is, and these elements are kind of like in a gas kind of, or plasma or gas form within this atmosphere of the sun. But what happens is the light has to pass through this gas, and then what happens is we get a certain amount of, so wavelengths or photons of light escape out from the core of the sun. But what actually happens is these atoms that are within this atmosphere of the sun that have been generated in the core, they actually absorb particular wavelengths of light. So you'll get something like this. So if you imagine, so for example, the iron here, so if we look here, so these lines here that are on the spectra for sun, they're associated with iron atoms. And what's happening is the iron atoms are soaking up these colors of light, or these photons of light that are coming out of the nucleus. And so that's what's happening here. And then you have, like, so you might also have, for example, magnesium in here as well, magnesium atoms. And the magnesium atoms are absorbing, for example, these wavelengths of light that are, within the green part of the spectrum. Then you'll have sodium, and it's absorbing the wavelengths of light that are, let's say, within this part of the spectra, for example. So you get these absorbed. And then you'll have oxygen, and these lines here are being absorbed by the oxygen atoms that are within the star. And what happens is the light, what's left up, what's remaining then after these atoms or elements have absorbed the particular wavelengths of light, the rest of the light actually escapes out of the sun, and it travels as white light. And then when we pass it through a prism, so essentially this is the effect. You have the white light being generated, let's say, within the core of the star. It's passing through this gas, this cooler gas here that contains all of these elements, and it's absorbing the particular wavelengths of light. Then that light comes down to Earth, and there's telescopes, for example, on the Earth. Imagine this is your telescope here. So these are your telescopes, and what they do is they look at the light and they pass it through a prism, and they look at the absorption spectrum that's generated, and they kind of get something like this for our sun, for the sun that we have. And what they can do is they can then identify, they can say, okay, I can see why we can study the starlight, and we pass it through a prism, we look at the colors of light that are taken out, and then from that we can identify the elements that are present here, let's say within the atmosphere of the sun. Now what they can also do then as well is they can take this, so imagine, so we take this spectra here, if I just put it here, and they can actually look at this spectra and they can create like a graph. So they can take a cross section of this spectra here, and they can kind of create something like this. So you'd have, let's say, you'll have a particular spectra, and you'll have, so let's say for everywhere so you'd have something like this. So everywhere, let's say that these lines are taken out. So imagine that might be sodium, these might be the lines for oxygen, and you get something like this. So what we're seeing here is this is absorption. So more and less. So what's happening is, let's say for calcium, so these might be the absorption lines that are associated with the element calcium. And what we can see is some of the light, let's say within this blue region that's associated with calcium, some of it's absorbed, but not all of it. Some of it does actually pass through. And what they can do is they can actually link, so let's say, so these might be the absorption lines, let's say the amount of this red light, for example, that's absorbed. So not some of it, like most of it is absorbed, but there is some of it that actually gets through. And what they can do is they can link this to concentration. So they can say, like, let's say, if you have, so the more, just as an example, the more oxygen that is present, let's say, within the star that you're looking at, that you're examining the starlight, the more of this oxygen light that's absorbed. So let's say the deeper these channels are. So let's say if the channel, I'll do this in red. So imagine the channel goes all the way right down to here, for example, right down to here. What that means is that in order for more of the light, the red light, to be absorbed, there has to be more oxygen present within the star. So what they can do is they can use mathematics and programs, for example, and they can examine like exactly how much. So we see that some of the red light is taken out because we have these bands, but what we can do is we can actually look and see exactly how much is taken out, as in like how much is absorbed. The more of the light that's associated with the particular element that's absorbed, the more of that element that's present within the star. And then what they can do is they can look at that, and then they can kind of figure out like how old the star is based on the amount of elements that it has produced. The higher the amount of elements that it's produced, the older generally the star is. And that's a way that they can kind of look at and date stars using this process that's known as spectroscopy. So they basically examine the light associated with stars. So hopefully that makes sense. That's just kind of a quick introduction to this topic or process of spectrophotometry is what it's called, or the study of light. So hopefully that makes sense, and thank you for listening.